Thrusters. Check. Shields. Check. Navigation. Check. Missiles. Check. Assembly is completed. Now launching the Phoenix.
Infiltrate the ones who took away your homes. Show them what they done, put them where they belong. Defeat the enemy of your mothers and your brothers. Rise above the virus in your culture. It takes one to start a revolution. It breaks us all to fall for the illusion. Corrupt the life, corrupt the life, and show the world they're a liar to the warrior.
Good evening, good morning, good afternoon, or wherever you're connecting to us from. Welcome to OWASP Ottawa's November meetup. Hope you're all staying safe and wearing masks and socially distancing. We're very excited to present to you this evening. And first, I'll hope you had a chance to look at our public service announcements. And I would like to introduce our first speaker. Dimitri is a long-term member of OWASP Ottawa. I've seen him at many of our our meetups, and he's been a presenter in the past. He's currently a security researcher with Vectra AI, and he's been in the industry quite some time. I'm not going to say how many years, but he's a builder, a breaker, a credit card taker, and he is passionate about all things security, and particularly in web and binary exploitation, reverse engineering, secure software development, cloud and networking, threat detection, and CTF competitions. Is there something you're not interested in security? Anyways, we're very pleased to have him this evening to talk about keys under doormats, problems and solutions for storing credentials in web application security. Welcome, Dimitri.
Thank you very much, Gareth, for that awesome introduction. All right, so let me share my slides. Hello, everyone. Really happy to be here. Hope everyone is staying safe. So, all right. Okay, I hope you guys can see my slides. So as Gareth mentioned, keys under doormats is the title, and we're going to be talking about problems and solutions for storing credentials in web applications securely. Who am I? Dimitri Berioza. Here are some of my contact information. If you have any questions later on or want to reach out to me. Currently a security researcher with Vectra AI, just like Garth said. Our company does on-prem and cloud network threat detection using artificial intelligence. So check us out. Prior to that, I was a pen tester with IBM X-Force ethical hacking team for a few years. And before that, spent over 25 years in software design and development. So I come from the builder background, and then I switched sort of into the breaker role. As Gar said, I have many interests. Reverse engineering is probably my biggest passion. And in my leisure time, CTF competitions are just awesome. So it's a lot of fun to do. This presentation was actually prepared together with my former colleague, Ron Craig, who's still at IBM Security. So before we continue, just a quick disclaimer. My current or past employers do not necessarily endorse this presentation. This is just my own personal research. And let's start with the agenda. So I'll start talking about what are secrets in general, what kind of secrets your application can store. Unfortunately, there are many incorrect ways of storing secrets, and we'll see some of those. And there are abuse methods for actually getting those secrets out and stealing them. I'll touch on how to properly store secrets in the application. Then we'll talk about something called master keys. I'll explain what that is. And I'll talk about storing them in the file system, which is kind of a novel concept if you're trying to do it securely. Then I'll introduce a small library that we built to help do that, and then we'll wrap up. So applications today, web applications in particular, pretty much all of them have to deal with different kinds of secrets. It could be user login credentials. You need to the username and password to log the user in. There are back-end system credentials where you need to talk to some back-end database or server. There are encryption keys, private keys for certificates. There are API keys. Those of you who do cloud development, I'm sure very familiar with those. And then there is, of course, sensitive customer data. In this day and age, it's becoming more and more important. It's very critical to store customer data securely. And there is actually legislation introduced more and more jurisdictions to safeguard customer data and hold software producers responsible if that data is leaked. So it's a very serious issue. And all this data must be stored securely, encrypted, both at rest and in transit. That means that at rest, where it's stored, let's say on disk or in database somewhere. In transit means when it's transferred over the network, with the most sensitive data being encrypted in use. That means that if you have, let's say, some very sensitive encryption keys and you store them in memory while your application is running, they should be stored there in encrypted form, then briefly decrypted just so that they could be used, and then encrypted again. So that's what in use means. So there are several terms that we'll use in this talk. Login passwords and credentials, they're a little different. Login password is something that human usually enters when they log into the system. But it's something that beyond that shouldn't be used in any way. So those passwords are usually stored in a way of one-way randomly sorted hash. So that means that they only needed to verify that the user logged into the system correctly, and then they're not needed after that anymore. Whereas credential is a secret that can be used to access some other resource, for example, some database system. And those you probably need multiple times. They need to be available in unencrypted form because that's how you will send them to that remote system. So careful measures must be taken to store them correctly. There's also a concept of data encryption keys versus key encryption keys. And the difference is that sometimes they're one and the same, but in carefully designed systems, they're different because let's say you have this a vast array of data that you want to encrypt and use data encryption key for that. And that key is then encrypted by a key encryption key. The reason for this two-stage system is that, let's say if you need to rotate keys, if you need to change your master encryption key, you don't have to go through all your data and re-encrypt it. You just can't change the master key and re-encrypt the data encryption key. So that saves you from these long periods of time where you have to wait for all of your data to be re-encrypted with a new key. And in this talk, we'll primarily talk about credentials and also the master keys because they kind of figure into this problem set. So in secure credential storage is very common. As I mentioned, I've done a fair bit of software development. I've also done penetration testing as a member of internal penetration testing team for IBM. So I saw a lot of source code for different products that IBM ships. And unfortunately, sometimes we see mistakes that are made by developers when storing credentials in the code. So the first one is where you just embed credential in source code in plain text. And I'm sure for many of these that I'm going to be showing, you've seen these in your practice as well if you're a software builder. Secrets are stored in plain text in configuration files, in plain text in databases, and in plain text in environment variables. Just no encryption at all. Sometimes people realize that this is a problem and they want to take some measures, and obfuscation is kind of the next logical step. So they try to base 64 encode their secrets. Sometimes they use XOR encoding with a constant key, which is easily breakable, easily reversible type of obfuscation. Or sometimes secrets get encrypted. They actually use an encryption algorithm, but the encryption key is constant and hard-coded. So if you look at this piece of Java source code, you'll see that both the initialization vector is bad. It's constant and hard-coded. That's your receiver is actually supposed to build a fresh one every time you encrypt. But what's worse, the encryption key is stored in the application source. And I'll explain why that's bad a little later. So why is this a problem? So first of all, plain text storage I think it should be kind of self-explanatory. When you store something in plain text, it can be leaked from the application in a variety of ways. And for all intents and purposes, both plain text storage and something that's encoded, let's say with XOR encoding or base64 encoding, they're essentially equivalent. This is not encryption by any standard. So it's pretty much equivalent to plain text data storage. If the data is encrypted, but the keys to encrypt the data are either hard-coded in the application or leaked, the data can still be accessed. The keys that are hard-coded, they're also hard to rotate periodically or to change in the event of the breach. So let's say you ship an application to your customer and something happens there. They get breached by, well, some gang, of which there are plenty these days, and they urgently need to kind of secure their data. As part of that, they realize that their encryption keys are probably all compromised now. They need to re-encrypt their data. If your encryption keys that you use for storage of your data are hard-coded in your application, you now have a real problem, because what are you going to do? You're going to have to ship a new version of your software. It's hard to do that when things get stored right in the application. So what are different ways that these insecure data storage can be abused? There are actually plenty. First of all, there's code analysis. Application source can be stolen. And I read some research that sometimes people can be kind of bribed into revealing internal company secrets for as little as a few $100s. So there's a research group that did that research, and they found that sometimes employees need to be offered very little money to reveal internal company secrets. So, and that includes source code. So somebody can just buy a DVD full of your source code off of rogue employee and have all your source, and be able to discover everything that's stored in kind of all the keys, all the passwords that are embedded in the application source. Applications can also be reverse engineered, and I mentioned this is a passion of mine. Reverse engineering is actually it's not a black art. It's very doable, and there are competitions ongoing about who can reverse a particular application faster. So it's something that people do as a sport. So it's very common, and black hat hackers will definitely do that if there's a chance that they can recover some secret that's stored inside the application code. There are also a lot of vulnerabilities. As members of OWASP, I'm sure you've seen a lot of these in action. There is path traversal, where somebody can, let's say, steal your key store, or maybe the application source. There is local file inclusion. There is XML external entity abuse, where you can form the XML blob in such a way that you force the XML processor to send you one of the files from the local file system. There are flavors of SQL injection that you can abuse to make it load a local file and ship it to you. And this is kind of an interesting one. In some systems, there's actually guidance that says that, well, to secure your encryption key, store it in the environment variable, and that way it will be safe. There's actually a class of vulnerabilities where you could, as part of stealing local files, you can actually steal on Linux. You can steal a local file that contains the environment variables for your current process. So if you happen to store your encryption key that way, and somebody stumbled upon this vulnerability in your code, you can lose control of that encryption key. And there are many others. So you can see that incorrectly stored encryption keys become sort of keys under doormats. So data is not encrypted or encrypted poorly. When it's encrypted, the key that is stored in close proximity to the data. That happens very often. So let's say you have a database and the contents are encrypted. That's good. But the encryption key that you used to encrypt the database, you store it in a config file on the very same system next to your application, if there's a bug in the application that allows exfiltration of that file, they could exfiltrate the config file that contains the encryption key, they can exfiltrate the database, and they have all your secrets. So in other words, often people either don't lock the door or lock it, but store the key sort of under the doormat, so to speak. So what are the proper ways of doing it? So first of all, in this day and age, it's really inexcusable to store sensitive things in plain text. You have to encrypt all your sensitive data. You cannot use obfuscation, and by that I mean base64 encoding, XOR encoding, and all these simple, very simple encoding schemes, and also custom-made encryption. It's really a dangerous thing when people start writing their own encryption algorithms. There's a famous cryptographer, Bruce Schneier, and there's something called Schneier's law, where he says that developing an encryption scheme that you yourself or your friends cannot break is really, really easy. Anyone can do that, pretty much. And you can try it. I'm sure you'll succeed. But the tricky part, the difficult part is to build an encryption algorithm that nobody else can break. And that requires years of efforts and testing by top cryptographic minds in the world to actually test and verify that the encryption algorithm is secure. So custom-made encryption is a big no-no. If you are thinking about this clever encryption algorithm that you yourself came up with and you want to use it in your application, please don't do that. Keys must be generated fresh for every installed instance. This is important because let's say you have a hard-coded encryption key. Not only you can lose control of that in the event of the breach, and there is no way to rotate that key, but also once it's lost at the side of one customer, now the hacker has that key and they can go to every other customer and decrypt their data as well. So these keys must be generated uniquely so that this could not happen. So it wouldn't this one compromise could not lead to many compromises. And just hard coding is generally a bad idea. The proper way of actually storing secrets is encrypted key stores and vaults. The passwords that I mentioned earlier, the login passwords, keys that are not needed in plain text, so you're not using them to access some back-end system. You're only using them once to let somebody into the system. That kind of information actually has to be stored hashed, but not just hashed. It has to be stored hashed. It must be a random salt must be added to the hash so that hash of the same password would not look the same for every instance of that password. So if you have several users with the same password, their hashes should look different from each other, and that's the role of the salt. And also, and a stretching algorithm such as PBKDF2 should be used to prevent brute force attacks, and this helps the defender prevents kind of brute force trying of the keys because it makes the decryption the hashing of the secret slower. So you cannot make that process fast by using a really fast computer and trying lots of different combinations. Stretching slows that process down significantly to prevent brute force attacks and attacks of just trying lists of known passwords. Essentially, we want to store data in such a way that attacker, if they were to get an encrypted copy of it, would not be able to read it. And there is something called Carecrops Principle. It's a great guiding rule to follow in your software development. And it reads as, a crypto system should be secure, even if everything about the system, except the key, is public knowledge. And I know from my software development experience, often you have these discussions saying that, this is probably insecure, but who's going to know that? who's going to know that we're using this particular algorithm? It's hidden deep inside of our application. Who's going to bother to look? If the stakes are high enough, the bad guys will actually spend the time and effort to find out everything about your application and break it. So assume, as you're developing systems, that everything about your system, everything about every algorithm that you're using is known to the attacker. And only the encryption, the key that you use to encrypt your data, is the only thing that will be hidden from the public knowledge. So in other words, if somebody were to fully exfiltrate both the code and the encrypted data of your application from your customer's site, that would still not cause information compromise if they don't have access to the encryption keys. That would be a properly designed secure system. But there is a problem, however. So let's say we do all that. We encrypt all our data, we take our encryption keys, and we store them in a password-protected key store. And as I mentioned before, there's a data encryption key that stores the data. There's a kind of a master key that encrypts data encryption key. That's called key encryption key. So there's this master secret that sort of kind of unlocks everything. And once you have that, you can decrypt all the other keys and you can decrypt all the other secrets. So the problem is, how do you secure that and where do you store that? So it's kind of a deja vu and turtles all the way down. If we store that key in plain text or hard-coded, then we kind of are back to square one. We have the same problem as before, because if somebody were to steal, let's say, a configuration file with the master key, the key store, and the data, then they can extract and reveal everything. So that's, again, a problem. So your, let's say, a path traversal bug in your software can crash your world, pretty much. If attackers can exfiltrate all the files stored. So can these key encryption keys, these master secrets, be stored safely? And this is the problem that a lot of developers struggle with. And I've seen this in many code reviews that I did. People often give up at this point and they say, well, I don't know what to do with this. I'll just hard code this master key and hope for the best. So I would see sometimes code like this, where there is, let's say there is a key store and the password to open that key store is right there in the application, or would be in the config file somewhere nearby. This is unfortunately not secure. The key encryption keys must be stored in such a way that they cannot be stolen from a known file. But is that even possible? So if you think back to all these other vulnerabilities that we talked about, it seems like attackers can steal a file from the system and they can take everything. So is there any way to do that? Well, actually, yes. There are actually multiple ways of securing this scenario, and I'll talk about that next. So the first one is, ironically, is not storing the key encryption key at all. And I'm not trying to be funny. It's actually a common thing that you will see in different systems. On your laptop, you may have a full disk encryption system, which when you boot up your system, you need to enter a password to unlock your hard drive. And if you do not have that password, you're dead in the water. There is no way you can recover the contents of that hard drive. That's this concept at work. Or another example is, let's say, Apple iPhones, where Apple designed the system in such a way that if you don't have the PIN number to enter into your phone, even Apple cannot recover your data. So that's how this principle is implemented. Your password that you enter is used as a basis for deriving that master secret that encrypts everything else. And then if you lose that, then your data becomes garbage. There is no way of recovering it. This is great. This works. However, in your web applications and your applications that have to run unattended, this is not really a feasible scenario. Who's going to sit there in the middle of the night and enter the password to start the system if it happens to restart? Nobody. So unfortunately, this doesn't help us in the context of web applications. Well, enter HSMs, or hardware security modules. They're specialized hardware devices, and they store encryption keys in this specialized hardware. This is available both on-prem, like in a data center somewhere, or I think pretty much all cloud providers provide that service these days. That there are cloud HSMs, and they're exactly for this type of storage, for storing your master keys. And the reason why this is secure is that you need an API call to interact with these devices. So if somebody is able to steal files from your application, they probably do not yet have the power to actually execute code and call these APIs in the context of your application. So this prevents the full compromise, because they can steal the data files but they wouldn't have the keys to unlock them. The difficulty is that HSMs are not really ubiquitously available. They're very expensive. The cost of deployment may just be too high for some applications. But by all means, if you have access to it, that's the right way of storing your master secrets. There are some software equivalents to HSMs. They're less expensive. Usually they're either part of an operating system, they're also third-party products, but they're kind of not built into all platforms, and there may be costs associated with their deployment and management. It's basically a separate system that may run on the same machine, but it's separate process. There are also key lifecycle management systems that are responsible for the full life of the key from birth to death. Also, there's certain amount of management that comes with certain costs. So not for every application it's feasible to do that. So what if this is your situation? You don't want to hard code things. You learned your lessons. You want to do things securely, but using a dedicated HSM is not possible for you. Are you kind of at the mercy of the attackers? Well, no. There are actually yet other set of ways of storing these master keys securely, and that is based on unique characteristics of the system that the application is running on. So essentially, we could derive these master secrets from certain system features that are hard for a remote attacker to figure out. Remember, we kind of assume that attackers they have access to vulnerabilities that allow them to steal files, but not necessarily do anything else on a system. So if you think about that, there are actually a number of unique IDs that come to mind, but unfortunately, none of them make good candidates for a variety of reasons. So there is a network card MAC address, and I've seen applications that actually take advantage of it and use it as a basis of generating your encryption keys and whatever else. The problem is that it's broadcast on the network and can be leaked. It's not a really unique. It's a unique number, but I think half of it is manufacturer dependent. So if attackers can guess the manufacturer of your network card, they have half the key, and the possible key space is so small that it can be brute force. So it's not a good candidate. There are IDs associated with motherboards, hard disk drives, CPUs. Again, key space may be small. Some parts may be manufacturer dependent. It may not even be available on a particular system. And this may be difficult to depend on in a virtual environment because your application may move around. So let's say you install it and the encryption keys are generated based on one CPU ID, and then in the cloud it's moved to another instance, CPU ID is different, and now your application is dead because you cannot decrypt any data. Your master encryption key does not match anymore. There are disk volume names, but again, key space may be small. They may be actually leaked through Unix, some of the Unix files, and that kind of puts us back into the problem with attacker being able to steal files. Also, all of these IDs are not generated in a cryptographically secure way, so there's too little entropy, and even if we wanted to change them, they may not be under our control. So it just doesn't make them good candidates. if it would be simplest to store that master secret we generate in the file system in some way, but it cannot be stored in a file that's known to the attacker because there are just too many ways to steal files. So if you're kind of listening carefully, then maybe you're kind of already have a hunch of what we're trying to propose here. So in our research, we found several methods to store the key encryption keys by utilizing features of the file system that are not easy to discover by reading files. That's basically the gist of it. And we'll outline two such methods. They're easiest to implement. So the first one is what I call secret folders. So with this method of storage, a subfolder with a random name is chosen to store master secret files. So you install your application, you generate a set of folders and files, and one of the folders is a folder with a randomly generated name. It would be randomly named on every system on which you install it. It should be a file system safe random string, and also it has to be a name that you would recognize. So it's a good idea to have some kind of prefix or suffix to it. And what you do is you store your master secrets, your key encryption keys, as regular files inside that folder. The application, when you implement it, can easily find that folder and load the key. You just do, let's say in this particular case, you do enumeration of all the files in the config folder, and you see the folder with the prefix cac. You know that this is the folder where your master keys would be stored. You open it and you load keys from there. And you know, if you're an application developer, you know that you can easily do searches in the file system based on wildcards. So that's how you would find that folder. Of course, folders and file permissions should be set so that they're inaccessible to anyone except the user account the application runs under. And when the application needs to, as I explained, needs to write or read these keys, it just searches for the folder and finds the file. The attacker, however, could not use any of the file extraction vulnerabilities they may have because they don't know where to look. So because this folder is randomly generated, there is no way for them, as they interact with the, let's say, a path traversal vulnerability, to specify the specific file name that they want to steal. So they may steal your data files that are encrypted, but they would have trouble stealing the actual master encryption keys. So to do that, they need ability to search files, which most of the time would require code execution vulnerabilities. So if attacker can somehow inject code in your application, they could do this. They could actually send a piece of code that would search the folders and find the keys. However, the problem is that if that happens, they already have a remote code execution capability against your application, and it's a game over type of event. Your application now is fully dead, fully compromised. And what's worse, that HSM that you, let's say, you depend on in this scenario is also compromised, because if I can run malicious code in the context of your application, I could inject logic in your application to talk to your HSM, and HSM would not know the difference. It would think that your application is talking to it, and I would be able to retrieve all these secrets that are stored inside. So to overcome this scheme, you basically need full application compromise, at which point there's nothing else that you can do that to protect you. So that's the simpler way of doing it. There is a more stealthy way of storing master secrets in the file system, and for that we propose using timestamps. Keys can several bytes in size can be distributed over the timestamps of multiple files created specifically for this purpose. So let's say we have a special folder for storing the key files, and for each key there will be one or more files created. Applications can interrogate timestamps of local files easily and retrieve these little bits of the key from the timestamps. Attacker, again, usually does not have access to file metadata. And again, short of having code execution privilege of the system, they cannot retrieve the keys. So let's see how this works. So suppose I want to store an encryption key that's 32 bytes in size, and we choose to store 2 bytes per timestamp. For that, we'll need 16 files, and those files could be just empty or garbage, doesn't matter, because the only thing we need is the timestamp bit, well, the timestamp portion of the file metadata. If you need to store multiple keys, you just create multiple sets of files, and they can just have, either suffixes or prefixes that indicate which key that is, key 1, key 2, or whatever. You need to, of course, in order to reassemble the key, you need to have some kind of order, so that we could load these files, the list of the timestamps of the files in a particular order in order to reassemble the key in a particular order. So some kind of numbering scheme also would be helpful. And there's some examples at the bottom here. So let's look at an example. So here is a timestamp, Linux timestamp for a particular file. So on the left, there is the actual timestamp that we're encoding, and on the right, there are 8 hexadecimal bytes that store that timestamp. Suppose we wanted to store a key that's 6 bytes in length. If we store 2 bytes per timestamp, we'll need three files, and we'll just embed bytes of the key in the timestamps. So as you can see, timestamps still look fairly reasonable, and you're able to store the secret information in the timestamp. You don't need a lot of space because, by definition, master keys are something that you that's your top level encryption key that you then use to recover everything else, including other encryption keys. So the size can explode at the next level. You just need a very little bit to store the master key. This is a more labor-intensive method. It's it's more stealthy, but it's more kind of on the obfuscation side, because people can discover your algorithms, discover how your application works. So we're not relying here on this method being secret. We're relying on the timestamps being inaccessible to attackers who have file exfiltration capabilities. So there's certain caveats. Some of the systems do not guarantee consistent setting of milliseconds. We kind of learned that the hard way. So it's better to use seconds granularity on the timestamps. We recommend changing only a portion of the timestamp so that the timestamps remain reasonably sane. So let's say if you just drop your full key as a timestamp into the file system, you could get a timestamp that's, let's say, 20 years in the future or 20 years in the past. There's no telling how the operating system or other applications may react to a timestamp like this. So it's better not to risk it. It's better to use a portion of the timestamp. Of course, care should be taken of in case of backup and restore. So because timestamps may change, and that's really a catastrophic event, because if that happens, you have no way, if you implemented your system properly, there is no way of recovering your data because everything is encrypted and the master key is lost. Also, running utilities that kind of globally modify timestamps is also a bad idea in this particular case. So we have to be careful. So what I just said about permanently denying access to data is actually sometimes used as a method for shredding data. You just, if you want to destroy data, you do not necessarily need to, let's say, wipe your hard drive with zeros. An alternative is to encrypt it with a good key and then just delete the key. And that's similar to shredding your data, because on a properly designed system, loss of an encryption key is a catastrophic loss. You cannot recover your data. There are probably additional ways of doing the same thing with other file system features. So feel free to experiment. And the goal is basically to have a method that's resistant to a variety of vulnerability types, and especially the ones that allow file exfiltration, that can only be defeated by attacker getting remote code execution capabilities, and the low cost, because that's the whole point of this thing. Like if you're a well-funded project, you're better off using HSM. This is the proper way of doing this. And I want to clarify this. I'm not advocating this method as a universal method. I had some comments and questions about that. No, it's not what this is for. It is to bridge the gap between the application that's currently insecure because it stores things in clear text or stores encryption keys insecurely, and the application that requires a lot of resources and costs to run because it needs availability of HSM. So there is we feel that it's possible to have a situation in the middle where you are secure, but let's say you cannot afford the HSM, you can still remain secure. And the method, of course, should be reliable in the presence of file system changes, another system changes. So we built this really small library that actually implements this functionality, implements these two methods. And it's an OWASP incubator project. It's called Sidekac. So basically, the two methods that I described are implemented as a Java library, and this is the URL that you can go to at the OWASP site, and there's some documentation there and the pointer to our GitHub repository. So that's the implementation of the secret folder and the timestamp techniques. It plugs into Java security infrastructure, so if you are working on a Java application, it should be fairly easy for you to just plug it in. It's designed as a security provider in the key store class implementations. We welcome bug reports and feature suggestions, pull requests. Feel free to contribute functionality, or tell us about any bugs you find. The repository is actually structured to have functionality in different languages. We didn't have the need for other languages in the projects we were working on, but absolutely you can do a Node.js implementation, a Python implementation, a C++ implementation. It's pretty much wide open. If you have a need for it and you implement it in another language, feel free to contribute. We'll welcome it. So what are the key takeaways? So it's very easy to store secrets insecurely. When I was going to school in computer science, they actually didn't teach us much about computer security. And from what I hear, things changed for the better these days, but they're not where they should be. So developers enter workforce not knowing how to implement applications in a secure way. So it's a very easy mistake to make, but that's why we're part of OWASP, and that's why we're learning about these things. Is we actually want to make things secure. We want to correct these problems. Special attention must be paid to proper encryption of data and of key storage, because there are mistakes that you can make there. There are a lot of vulnerability types that help achieve system compromise, and in particular, the ones that allow you to steal files, because that's where the customer data is, that's where the encryption keys are. So it's very easy to, if you have that kind of vulnerability in your web application, attackers can steal all your, basically the keys to the kingdom, and all your prized possessions inside, all the customer data and everything of value that your application stores and works with. Master keys suffer from the same problem of insecure storage as other secrets. So there's kind of this recursive problem of what do you do with a master key. And I talked about different ways of protecting master keys, proper ways. And unfortunately, a lot of these methods are not free. They require a lot of maintenance. They require additional hardware, human resources. So I realized that not every project, not every web project yet can take advantage of it, but should if they can. So if you're in an environment where you you do have access to these technologies, these are absolutely the proper way of doing this. But if you are kind of looking for a poor man's version of secure way of storing the master encryption keys, consider what we're proposing, because it will help protect you in the face of file system file exfiltration vulnerabilities in an inexpensive way. You don't really have to. It's just a little bit of code that you can add to your application. And that's the end of my talk. Thank you very much for listening. I just wanted to thank some of the people that contributed to this work, my former colleagues. And if there are any questions, I'll be happy to answer them. And if not, thank you guys for listening.
Awesome. Thank you so much. Thank you for hitting so many trigger words in my career. So I had a couple of questions, and the first thing that you mentioned was that sort of struck me was the fact that some employees will cough up extremely private details about their source code for little money, and that sort of is the lesson here, that employers should pay their employees who know this well and treat them nicely, or is there something I'm missing here?
No, it's unfortunately, it's known that in security, the human problem is the biggest problem. I think by statistics, almost half of the attacks come from malicious insiders. You have rogue employees, like let's say you have an IT guy that's disgruntled, like they can do a lot of damage. And really, all the serious compromises start with somebody clicking on a link in an email that they received. So it's really a human problem. A lot of serious breaches come hand in hand with elaborate social engineering. So it's unfortunately I don't know if we even will get there at some point in the future, but I don't really have good answers for solving the human problem. Of course, you have to treat your employees well. You have to do employee education. It's a constant struggle, but it's really, really tough. You have to compartmentalize. You have to make sure that people don't are really on a need-to-know basis. You have to kind of give as little privilege to each individual employee as they need and not more. Like there's all these little things that you can do to make things better, but ultimately it's a tough problem to solve. I think maybe I'm a pessimist.
Yeah. To the social engineering aspect of it, I watched a program that talked about a company that did a debrief of employees under the auspices of a interview. And so these people, these targets of interest would be brought into a fake office, and they had done it, even the fake family photos on the desk and the whole 9 yards, and they would be brought in for an interview. And what the target did not suspect was that it was actually a debrief. It was very well done. I was shocked. I now am very nervous in interviews, but the second thing is that you mentioned about developing what I called a systemic key, and that is a deterministic key based on system parameters. And so you mine a system for some sort of uniqueness to generate a key that you would use as a master key. And I've been down that road. And you talked about using the MAC of the NIC in whatever system as a potential source of uniqueness specific to that system. And not only does it cough up all the information that you talked about, but even worse, if you rely on it, some systems will turn off their NIC if it's not actually plugged into Ethernet to save energy, particularly in laptops. So imagine the scenario. It's a high-powered demo to a sales team in Japan. The salesperson has the demo set up. It's all running nicely. They then unplug the NIC and run into the next boardroom where the assembled people in Armani suits is about to evaluate the product. And it face plants because it can't find its master key because the system turned off the NIC.
Yeah, Yeah, and I hope it was clear. I think this is a wrong way of doing about
Very
it.
wrong, very clear, very wrong.
Yep.
Awesome. Anyways, I really appreciate that because I really enjoyed listening to the system that you proposed, and it's definitely something to consider. I'm just wondering right now, cynically, how many HSMs use that system? Something to consider. Maybe you should build HSMs. Anyways, thank you again so much, and we'll introduce our next speaker. Let me make sure I've got this set up right. There he is. So I don't know, maybe somebody out there has heard of something called Kubernetes. But just in case you haven't, we're very, very happy to have Magno Rodriguez talk to us about Kubernetes and security. He is a security specialist at Trend Micro, and he claims to focus on container and cloud security. But if I know any security people, he's probably focusing on a lot of other things too. I'm probably. We had some comms issues to begin with, so unfortunately, he's probably going to have to listen to me slaughter all the names that I'm about to pronounce here because I didn't have a chance to practice them in advance. So he is the founder of OWASP Paraíba chapter and the Jampasec Security Conference in Brazil. He's a speaker at many of these conferences, such as LongCon, which is in Canada, and RoadSec SP and B-Sides SP. I'm not sure what the SP means. You're going to correct me on that one.
São Paulo.
São Paulo. Awesome.
Yeah.
Good. And let me continue to slaughter this. Mind the Sec RJ?
Yeah, Rio de Janeiro.
Rio de Janeiro, right. Yeah. Okay. And OWASP AppSec Latam, so Latin America.
Yeah.
He's presented at BHAC and Just for Meeting in Portugal. And he's studied security and computer forensics at TC3 in New York. And he has he has more certifications than I can actually count. So I won't go into actually talking about all of them. So welcome. Thank you for joining us. We're very happy to have you with us.
Thank you, Gareth. Let me just share my screen here. Okay, can you guys confirm that you can see my screen?
Not yet.
No. No, it's okay. I can see on the stream. All good? All good. Okay, awesome. Yeah, so, okay. Today I'm going to talk about Kubernetes and give you guys a little bit of overview about Kubernetes security. So that's why this talk is called Kubernetes Security 101, some best practices to secure your cluster, right? So yeah, thank you, Gert, for the introduction, and I'm happy to be here at the OWASP Ottawa chapter. I'm a big fan of OWASP for a long time, and one of the reasons that I joined application security, that's because of OWASP, right? So yeah, just a little bit about myself. I'm an information security specialist at Trend Micro, right? Member of the cloud and container security research team. I don't consider myself a Kubernetes security expert yet, but I'm working to get there. And I'm taking the CKA, the Certified Kubernetes Administrator certification soon. And I don't know if you know about this, but this week it's happening the KubeCon North America, which is the major conference about Kubernetes and all things cloud native. And also they just released the CKS, which is the Certified Kubernetes Security Specialist certification there as well. So, but you need the CKA, so it's a prereq. So yeah, I'm looking forward to get that soon, probably next year too. Okay, so without further ado here, our agenda for today is I need to give you a little bit overview about Kubernetes. I know that it has become very famous around developers and container orchestration solutions. There are other solutions out there that I'm going to mention here, but Kubernetes is by far the most used one. And I'm going to talk about the Kubernetes architecture. How are the different components and different systems, they talk to each other. It's a very complex system, so it's important for us to understand this so we can go into the security part. For the security here, I'm going to talk about the control plane, which is one of the parts of the Kubernetes there. And I'm going to mention about the API server and etcd. I'm going to mention about the role-based access control, or RBAC, which is the solution that Kubernetes uses to control access to their namespaces and clusters and all the objects that it has there. Also, I'm going to mention about the worker nodes, some components there which are important to know and secure, the kubelet, and of course the pods that we're going to have there, network policies, and pod security policies, and last but not least, the audit logs. Okay, so what is Kubernetes, right? So like, what is that a lot of people are talking about, right? Is it a competitor for Docker or something like this? Like some people, oh, should I use Kubernetes or should I use Docker? There is no such question, right? So Kubernetes is an open source system for automating deployment, scaling, and manage of containerized applications. So by containerized applications, you can guess that Docker applications are containerized applications as well. So Kubernetes uses Docker engine by default to run its containers, right? So it's just when you have Docker, right, you have one image there. It's easy for you to manage and control. But when you have a cluster and you get into like hundreds or thousands of servers and you have hundreds or thousands of images, it's hard for you to manage that manually with Docker, right? So Kubernetes is originally developed by Google in 2014. It was based on two projects, internal projects from Google called Borg and Omega, right? And it's developed in Go language, right? As many of other projects from the CNCF, the Cloud Native Computing Foundation, which I'm going to mention in the next few slides. And now Kubernetes was donated by Google to the CNCF, and it's maintained by the CNCF now, right? So just a fun fact here, the Kubernetes comes from the Greek, which means helmsman or pilot, which is an analogy, right, for the pilot of the ship that takes the Docker containers in the ship, right? And the first question you may ask yourself is like, why Kubernetes? Why should I use Kubernetes? Should I use Kubernetes to run like a simple website, a static website for my company, or why should I use that, right? So that's why I brought this comic here, because Kubernetes is a complex system. At least from my opinion, it's hard to understand at first. There are many different components talking to each other, and it's very easy to make mistakes if you're not following the best practices, right? So it gives you the freedom to change many components and many configurations there, but it also allows you to make mistakes more easily, right? So one of the things that you should think about is why should I use Kubernetes, right? So do I really need that, right? And there are other options out there. Like I mentioned, there's some Apache Mesos from Apache, Docker Swarm, right? And Red Hat OpenShift are some other solutions that can help you manage containerized applications, right? So yeah, you have to really think about if you have not just the need for Kubernetes, but also people train in your company or like a third-party consulting company that you're hiring that will be able to like deploy and maintain those clusters, that infrastructure, right? And what is the CNCF that I mentioned, right? So the Cloud Native Computing Foundation is a sub-foundation of the Linux Foundation, right? So basically, it's an organization, a non-profit organization that creates sustainable ecosystems and promotes communities to support the growth and health of the cloud's open source software. So what that means is the open source projects and software that are used by many companies, and it's used in the cloud, mostly in the cloud. And they kind of maintain those projects, they help and they fund so that they can keep up to date, they keep being developed and improved. And so they have many different projects as I'm showing here. So like Prometheus, Envoy, Core DNS are just some examples. If you check out that link on the slide below, you're gonna see the landscape of the Cloud Native Computing Foundation is much bigger than that. So I didn't add in the slides because it wouldn't fit here. So yeah, many different projects, and that they're all open source. You can easily adopt them to your organization, or you can help contribute to those projects as well. And what is cloud native, right? What does that mean, right? So the definition of cloud native applications, according to the CNCF, is that applications that they have those 7 characteristics here on the left. So they need to be scalable, dynamic, resilient, right? And all those things. Some examples of those applications are this on the right here. So containers, service meshes, microservices, immutable infrastructure, and declarative APIs, right? So cloud native technologies, they empower organizations to build and run scalable applications in modern, dynamic, and environments, right? So that's why we're talking just to give you an overview, because Kubernetes is part of this ecosystem, and it's considered a cloud native application. It's part of the CNCF, right? Okay, good. So just to give you an overview about the architecture of Kubernetes here. Let me just check. Okay, good. Okay, so we have 2 main components in a Kubernetes architecture, right? So we have the master node and we have the worker nodes, right? The master node on the left and the worker nodes on the right. And the master node can also be called control plane, right? And inside that control plane, you have at least the 5 main components there. As you can see, the Kube API server is there in the middle, and it's the one that communicates with all the other components, right? So the Kube API server is basically an API server that's responsible for exposing and receiving API calls, right? Below the API server, we have the etcd, which is the database or the data store where Kubernetes saves all the internal information, right? So which nodes are part of the cluster, which resources exist in the cluster, stuff like that. On the top left here, we have the Kube Controller Manager, which is responsible for many different internal tasks on the cluster. So things like noticing when a node's not responding, or maintaining the correct number of pods, right? So it has like the Kube Controller Manager. Just people joke that, like any manager, the Kube Controller Manager doesn't do its job. It has different controllers inside it, so smaller components that really do the checking of those verifications, right? So you have like the pod controller, the service controller, and stuff like that. So yeah, and on the bottom right here, you have the Kube Scheduler, which is the one that really decides where Kubernetes is going to execute the pods that you want to run. And I'm gonna get into pods in a second on the next slide. And on the top right of the control plane, we have the Cloud Controller Manager, which is the one, the component that interacts with cloud providers, managing resources such as like load balancers and disk volumes, okay? On the other side, on the worker nodes, you have at least 3 main components there. So you have the kubelet, which is the agent responsible for managing the container runtime engine and executing the containers itself when necessary, right? So and collecting information about execution, so like telemetry data, right? So you have the scheduler on the master node that tells the API server to create a pod, for example, in one of the nodes. The scheduler is going to decide, and then the API server would like forward a request to one of the kubelets on the worker nodes to create the pod and start the containerized application that you want, right? You also have, you also have the kube proxy there on the worker nodes, and kube proxy manages the communication and network communication, allowing that different pods and different containers communicate with each other, and also responsible for the external requests. And you have the container runtime, like on the worker nodes here, that is the by default is Docker, right? As I mentioned, and is the one that really creates the containers and like executes the application, right? So you have by default is Docker, but you can have other ones. You can have Container G, you can have Cryo, or you can have Podman. They're easily changeable, and you can configure those. Okay, that's it for the architecture. On as I mentioned about pods, right? So there is a distinctive there's a distinctive term and very specific to Kubernetes, pods. And in Kubernetes, pod is the smallest unit that you can have on a cluster. So it's not, you cannot create a container itself without a pod, right? So it's kind of like an object that encapsulates the pod. But the difference here is that you can have more than one containers running on the same pod. So you can have here, just like the picture there, one or more containers running on the pod. So you can have one by one-to-one pod to container, but you can have more. Usually they're called like sidecar containers that may collect logs or telemetry data of the main application, the main container application there. And also, so the pod is a Kubernetes object, right? But usually you don't deploy pods by itself. You use another object that's either like a replica set or nowadays a deployment that creates a replica set that creates the pods. So because the deployment is responsible for like scaling the updates and rollbacks on your cluster, for example, if you create a deployment and a pod goes down, the deployment is going to notice that because it's constantly checking the Kube API server, right, for that, and it's going to spin up another pod for you to make sure that your cluster is always reflecting what you have configured before, right? And you also have namespaces, which is basically a logical separation between different projects on the same cluster. So different from, do not confuse that with the Linux namespaces. Here it's the Kubernetes namespace. So think like the namespaces here as like a folder that you have different projects. So you could have like a dev project, a QA project, or a QA cluster and namespace, and a production namespace for your project, right? And nodes are basically the servers, the VMs, or the bare metal servers that run your Kubernetes applications, right? Okay. And in Kubernetes, you have many different objects, API objects, as it calls. And we're not going to go through them all here because we probably don't have time. But as I mentioned, we have the pods, we have replica sets, daemon sets, right? And each one of those objects, they have a specific a function and goal. So you need to understand them so you can know which one to use best for your scenario, right? So for example, if you just need a pod to execute one function or something very quick, you can create a job, which is basically a pod that does an action and completely like stops, right? If you're going to execute that frequently, you can create a cron job that does that action, and you can configure it just like the cron on Linux. You can configure it to run, for example, every day at a certain time, right? You have config maps, which is basically an object to store configuration settings. And you also have secrets, which is another object to store sensitive information like credentials and API keys and stuff like that. And I'm going to mention a little bit more about secrets in the next few slides. Okay, so this is basically the Kubernetes objects. They're all, they can be written in JSON or YAML, which YAML manifest, which is the most common way to use them. And this is basically an example here of just how you start writing Kubernetes objects. So you have to say the API version, you have the kind of object that you want. So the object name would be one of those API objects here, and then you can add more information there, right? Okay. So, and how do you interact with your cluster, right? So how do you control Kubernetes? How do you manage that, right? So just like Docker that has the Docker command line for you, the Kubernetes has the kubectl or kubectl or kubecontrol. I'm not going to get into the discussions about the name here, but I like to call kubectl, which is the CLI tool that allows you to control your Kubernetes cluster, right? So you have, when you create a cluster, you usually have, you get a config file that you save on your home directory on the .kube directory there. And just like I've said, similar to the Docker CLI, the containers for Docker containers, you can use the syntax to interact. So if you use Docker before and you're familiar with the Docker CLI, it's going to be easy for you to use the kubectl commands as well. Okay, good. So I think that's it for the introduction about Kubernetes and how to use it. If you've never heard about Kubernetes before, that's good. So I hope you understand. But if you don't, feel free to ask any questions at the end. But now we're gonna get into the security part, right? So what are the best practices? How do I protect my cluster? How do I make sure that my API server is not exposed to the internet? How I make sure that my applications that are running in my cluster are protected, right? So one of the main things about protecting a system is making sure about the integrity, right? So one of the basic things that you can do to secure your control plane, if you have access to it, right, is to perform some kind of integrity monitoring with for the most critical Kubernetes files, right? And the CIS has a Kubernetes benchmark. So CIS Kubernetes benchmark, that's a document that was released before, with some best practices and guidelines on which are those files that are important for you that you should monitor. So I brought a list of files here just for you guys, and it says like which permissions and ownerships you should have on those files, and in case if any of those change, right, you should get set up an alert or something. You'll get a message, so you should monitor that like something is going on in your cluster, somebody's messing with your cluster files, right? So those are by the recommendation of the CIS benchmark. Those are also the default values when you install a cluster on version 18 using like kubeadm. There are many different ways to create a cluster. kubeadm is the most common one. So yeah, if you have a cluster and you have access to the master node, for example, right? Because if you're using a managed services like GKE, EKS from AWS or AKS from Azure, you usually don't have access to the control plane, and we're gonna get that in a second. So you can't see those files, you can't verify them, right? So you're gonna have to trust your cloud provider there. Okay, so when you install Kubernetes, by default, you have 4 namespaces. As I said, the namespaces are basically directories for your projects and your Kubernetes applications, right? So the 4 namespaces that you have is the default one, which is basically the default for any objects that you don't set any namespace. They're going to be created there in this namespace. You have the kube node lease, which is, let's see here, which is the namespace for like lease objects associated with each node, and improves the performance of the nodes, heartbeats as the cluster scales. And you have the kube public, which is its namespace created automatically, and it's readable by all the users. So very important there to not store anything, any sensitive information there. But the most sensitive namespace that I want to mention here, I want to highlight, is the kube system namespace, right? So the kube system namespace is the namespace that that the Kubernetes objects are created, right? So for example, all those components on the left side, on the master node, the API server, etcd, and kube scheduler, and everything else, they are created in this namespace, right? So Kubernetes uses Kubernetes to run Kubernetes, right? So it's kind of an inception here, but yeah, they're basically pods that are running on your cluster, and they're just on a different namespace, which doesn't have a lot of security boundaries. So it's just a different namespace there. But you can see, we're gonna talk about RBAC, and I'm gonna mention how to try to avoid any access to this pods running on this namespace, right? So yeah, be very careful with the kube system namespace, which is the main namespace for your cluster. And then next you have the kube API server, right? As I mentioned, is the central API server for all the communications, not just from the master node, but also from the worker nodes. As you saw in the diagram there in the architecture, the kubelet and the kube proxy also communicates with via the API server. And one of the most common things that people do, or common mistakes that happen, is that when you create a cluster, you expose that cluster to the internet, right? So people without access, without permissions, can make a request to your API server, right? So just like the Docker daemon API, if you expose the Kubernetes API server and it's like a misconfigured cluster, people might be able, attackers might be able to exploit that, and depending on the permissions available, if they have like an anonymous user or they have some credentials there, they might be able to create pods, delete pods, or read secrets on your cluster, right? So here, just basically a simple command that you can use to see if your cluster and your API server is exposed to the internet here, right? Even if I got here like a 403 forbidden error, right? But I was able to hit the API, so maybe this shouldn't be exposed there unless I'm like, it's restricted to my IP address, right? So on your organizations there, make sure that you check that the API server is not exposed to the internet, that you can only access probably through the company VPN, right? And if you're using any managed services, make sure that you know which are the default settings of those managed services. For example, EKS on AWS by default exposes your the API endpoint of your API server, right? So if someone knows that URL, they can maybe request your API server. And how do I know which settings are enabled on my kube API server, right? So as I said, the CIS Kubernetes benchmark recommends some specific security settings for applying to your API server. And out of those 35 security settings that are recommended by the CIS benchmarks, only half of those are enabled by default, right? On version that I tested was version 1.18.5 for Kubernetes cluster, and only half of those were enabled on my cluster by default. So be very careful with that. Understand which settings are enabled and which settings are not. You can easily use this command here in the slides to check which settings are enabled, and if you have access to the control plane, right, you can change those settings and restart your API server with the proper settings. And another thing that Kubernetes has to protect yourself and just to manage all the access, right? So you're gonna have a cluster, and you might have different projects on with different developers with managing different namespaces, right? So it might get messy real quick, really easily, right? So Kubernetes has a role-based access control, just like any other web application out there, where you most of them use these already. Like you have a user, you have a manager, and you have an admin. So there are different roles for a specific application that lists different permissions that you have. Kubernetes also allows you to configure who can access what in your cluster, right? And it's enabled by default on the latest Kubernetes versions. You can check that by checking this flag on the API server. So from the previous slide here, where I executed the command, so there is authorization mode node RBAC here, which shows that RBAC is enabled on my cluster, right? Same thing, same command there to know. And how does RBAC works in Kubernetes, right? So basically, you have 4 different objects that you can create on your cluster to manage those access and permissions there. So basically, you have a role object, which is an object that contains rules that represent a set of permissions within a namespace. So you have like verbs and objects, right? So you can see like create pods, list secrets, and stuff like that. So you can define verbs and objects so you can set those permissions, and that object would become a role, right? So it's like kind of a role in your cluster, right? And then you have a role binding, which is basically another object that binds that role with a set of users, that would access those, would have access to those roles, right? So that's the basic permissions and these 2 objects there. And the difference here is that on the role object, you only have access to the namespace level of a specific cluster or a specific namespace, right? So it's restricted. Those permissions that you have on that role, it's restricted to a specific namespace. But if you want to give more permissive permissions, right? So you have the cluster role object, which applies those permissions on a cluster level. So the permissions that you give to someone there would apply to all the namespaces on that cluster. So basically, the cluster role is the same thing as a role object, but with more generic, more broad permissions, right? And you also have the cluster role binding that binds that role with a set of users that you want. And just a quick note here, Kubernetes doesn't have user objects, right? So it relies on other solutions and other integrations so that you can manage users for you. So you can't create a user object. You have service accounts that are specifically used for components on the Kubernetes to communicate with the API server and doing other things, but you don't have a user object on Kubernetes itself. Okay. Let me see how I'm doing on time. Okay, good. So you also have the etcd, like I mentioned, which is the main data storage location for your cluster, right? This means that all of your cluster objects are saved here. And here it's important to mention that Kubernetes has 2 ways of like receiving and configuring your cluster. You have the imperative way where you tell like, okay, kubectl create secret, kubectl create pods, right? So you have that way, or you have the declarative way where you can just create like a YAML file, a YAML manifest, like I showed in the beginning, and you just tell the API server, like, do this. This is what I want. This is the structure. I want this this number of pods in this number of X number of applications running on my cluster, and Kubernetes will has a knowledge of handling itself, understanding that configuration, and making sure that what you told on that configuration file is represented on the cluster, right? So for example, if you want 2 pods of Nginx running, right? So it's going to make sure it's going to store that information on etcd, and it's going to tell the scheduler, create 2 pods of Nginx, because that's what it's provided in the configuration, right? Okay, so one of the things that you need to be careful about the etcd, right? So it's treated like a database, right? Similar to the database for your application that you usually you probably shouldn't expose to the internet, right? And I hope that you don't do that. The etcd shouldn't be exposed to the internet either, right? So just like exposing the API server, exposing the etcd has an API as well that people might use it to communicate with the etcd and compromise your whole cluster. For example, if I have access to an etcd and I can alter the configuration files or the objects or anything there, basically, I can become cluster admin. I can create like a user or some permissions there on my cluster and say, okay, now I'm cluster admin, right? So basically, we've seen this exposed like 2,600 exposed etcd services on Shodan earlier this year. So be very careful when you're like, you shouldn't be exposing your etcd for any reason to the internet. And the 2 main things that you need to worry about on etcd is the encryption in transit, right, which is done by default on the latest versions of Kubernetes, right? If you check that with this command there, you can see that there is a cert file and a key file that are set for your etcd. And the encryption at rest, right, it's not set by default. So that's the big problem here, right? So all your configuration settings, all the state of your cluster is stored on a database and in plain text, right? So to do that, to do the encryption at rest, you need to create an encryption configuration object, which is another Kubernetes object that tells the etcd which components, which objects you want to encrypt, right? So for example, if you want to just protect your secrets and you don't care about other stuff, you can tell you can create this object and tell Kubernetes to just to tell the etcd actually to just encrypt all the secrets that are stored in the database, right? So be very careful with that. The Kubernetes by default, the etcd is not encrypted at rest, and it's all saved in plain text. Okay. And also, just one thing to mention about the secrets is that even the secrets is not right now is not a good way to store sensitive information, because if you're not encrypting your etcd, the secrets are only stored on your etcd base 64 encoded. So you know that base 64 encoded can be easily decoded. So that's not a very good way to protect sensitive information like keys, passwords, or API tokens, right? And you also have another object that you can use to protect your Kubernetes cluster. So by default, all your pods can communicate with each other on a cluster, right? So it's just like a flat network. All the pods can communicate with each other, right? So you need to have a way to like create a kind of a separation and make sure that only some of the pods can communicate with each other. So that way is the network policy, right? So to do that, you need to have a proper CNI being used on your cluster, which is the container. It's the container network interface. Oh, yeah, that's network policy. Okay, that's right. So, for example, really does the front end needs to talk to the database on the pod, right? So should it talk with the back end first, and then the back end talks with the database, right? So that should be usually the right way to do it. So you can create a network policy telling that, okay, the front end application shouldn't be able to communicate with my database, because if the front end is compromised, I can at least minimize the impact, right, and the attack surface of the attacker there, so he wouldn't be able to reach my database directly, right? So you would have to compromise the backend to be able to compromise the database, right? And another thing, like I mentioned, be careful with the kube system namespace, right? Because what if an attacker can access those pods on the kube system namespace, right? They can basically change any configuration, any security settings there, and compromise your whole cluster, right? One of the things that you need to be aware of when using the AWS Kubernetes Managed Services, EKS, is that the EKS network plugin by default doesn't support network policies. So you wouldn't be able to do that right now on AWS network policies. But recently they announced that they made security groups for pods, which is basically the well-known security groups on AWS that you use to protect your instances and like redirect traffic and stuff like that. You can use that now for pods, because before you could only apply that to an instance, which was a node from your cluster, right? But now you can go on a deeper level and create specific security groups for each pods that you have on your cluster. So that's nice. Talking about the worker nodes now, almost done. Same thing here applies to the files and integrity of those files and the recommended ownership and permissions, right? Just like the master node, there are some specific files on the worker nodes that you need to be aware of and protect those and get some like alerts if they are changed by anyone, right? So that's basically it for the worker nodes here. And the kubelet, which is the agent that runs on each node of your cluster. And although I didn't show in the diagram architecture, on the master node, you also have a kubelet and a kube proxy as well running there, right? We usually, even on the official Kubernetes diagram, they don't show that because technically you're not supposed to run your applications on the master node, right? That's not recommended. That master node is only for the Kubernetes pod itself. But to run the Kubernetes pod, you need the kubelet and the kube proxy as well, right? So basically the kubelet makes sure that all the containers are running in a pod. And the main security settings that you need to be aware of here on the kubelet is restricting the kubelet permissions and rotating the kubelet certificates, right? And for the pods itself, right? So the pods that are going to run your container applications, there are three main things that you need to be aware of. One of the main things is just like the Docker, you need to limit the resources that your pods are going to use, right? So for example, CPU and memory, you need to tell how much or how many CPU and memory those pods can use. You can do that in a pod by pod basis. So like on each pod that you create, you tell their resources limitation there. But you can also create an object that's called a resource quota that you apply that to a namespace or to the whole cluster, and it's going to limit all the pods on that namespace or the cluster to those limits for resources, right? Another thing is apply a security context, create and apply a security context, right? What is that? What is a security context? It's basically a group of security settings that you can apply to a pod, right? To enable or disable some permissions, some security features, right? So for example, if you don't want your container being able to escalate privileges, right? So there is a setting for that, the allowed privilege escalation, which should be set to false. The read-only root file system is another setting that you tell that the root file system of the container is read-only, so it's not writable, right? And the other one, just an example here, is run as non-root. So you set it to true because you don't want your container running as the root user, right? And the other thing, which is also part of the security context, is make sure that you're using those Linux kernel security features. Some of them, the three of them here, the SecComp, the EpiArmor, and the SC Linux. So SecComp is used to filter a process system's calls. The EpiArmor uses a program profiles to restrict the capabilities of individual programs, right? And SC Linux applies some security labels to objects and evaluates all the security relevant interactions via the security policy, right? And I know that by now you've already like, oh my God, this is a lot of information. How I'm gonna protect my cluster, right? So there is a easier way to do that, but I wanted to show you all the components and all the possible ways. So what you can do is you have a pod security policy. A pod security policy that's basically what we call an admission controller, and also an object that you apply all those security settings that you want, all different ones here on the slides that you want, and you apply that to your cluster, and all the pods on your cluster must have these security settings, otherwise they won't be able to start. So the admission controller, which I haven't talked about much here, but, and I'll try to give you an overview. It's basically an object that verifies all the calls to the API server. And for example, you have the authentication part of the API, you have the authorization part, and before you can do anything, for example, deploying a new pod or a new container, the admission controller checks some features and some configurations, right? So the pod security policy is one of the admission controllers that you can have enabled on your cluster. It's not enabled by default. That will check for those security settings. Almost done. And for last but not least, here is the audit logs, right? So Kubernetes is constantly checking the state of the cluster and the Kubernetes itself, if the pods are running and everything, right? But for a security perspective, you don't have a lot of information there, right? So the audit logs are not enabled by default, and it's highly recommended that you enable them for not just for security, but also for troubleshooting as well, right? And to do that, basically you need two things, right? You need a log path, right? So where you're going to store your log, it can be directly on your master node. It can be on a centralized server, which is the best option. And you also need a policy file, right? So what are you going to log? What is kind of the information that you want it to log, right? So you set those set those on your Kube API server configuration, right? And then Kubernetes restarts the Kube API server, and it's going to start logging information for you, right? So basically you have 4 audit policy logging levels. You have the none, which doesn't log anything. You have the metadata, which just logs the metadata of the request. You have the request level, which basically logs the metadata and the request itself, and the request response, which logs metadata, the request, and the response of the information, right? So just an example here, and you can give different logging levels to different objects and different information there. This is just a simple example of a policy that logs all the metadata of your cluster, right? And on managed services like EKS, that's easier to set up. Basically, it's just a button there that you do on your control plane. For example, here, you just set enable to enable the audit logs, and all the Kubernetes logs are going to CloudWatch to like, so you can search them there. You can send to a centralized server. You can send them to S3 or something like that, right? So it's basically the JSON logs are going to go to CloudWatch there. So yeah, those are not enabled by default either. And I think if you enable those, you're going to pay for the CloudWatch logs that you're going to use, right? So just to wrap up here, don't forget about the basics. I know it's a lot of information, a lot of different settings and configurations that you need to apply on your cluster, but don't forget about the basics, right? The basics are important. one of the things is update your Kubernetes environment version early and often. So Kubernetes releases a new version every 3 months. So make sure that your cluster is at least, if not on the latest version, at least 1 or 2 versions behind, but not too far behind, right? Don't use your cluster admin for your daily activities, right? So daily work, treat like a root user, right? Because if someone gets access to that cluster admin, it can do anything on your cluster. If you can, use managed services like AKS, EKS, or GKE, and I'm going to tell you why. Unless you have some specific business reasons or compliance reasons that you're not able to run those managed services, right? Then yeah, of course, do deploy your Kubernetes cluster on your own. But if you don't have that, those services provide a lot of better security defaults for you. So for example, you don't need to worry about the control plane and all the settings that I mentioned here. And also some of those managed services, they don't even charge you for the control plane. They only charge you for the worker node. So only the instances that you spin up and use on your cluster, right? And of course, check out the CIS Kubernetes benchmark document for more security best practices. It's a very good document. It's very extensive, but it's not. It might be scary at first, but it's basically because it's very detailed. So if you take some time to read it, you're gonna see that, oh, that's easy, because some of the stuff they just show you, oh, if you have this, here is how to fix it, right? So they're very detailed there. So I really recommend checking this benchmark. Let me see how I'm doing on time. Okay, am I good? Let's finish here. So yeah, just one of two things to wrap up here is the Microsoft released Kubernetes threat matrix earlier this year. I think was in April, where they, based on the MITRE ATT&CK framework, right? So they create all the tactics and techniques that people can use, attackers can use to compromise your cluster. So it's a good tool to use that and maybe do some red teams or some practice scenarios to see if your cluster is properly protected. It's not an official MITRE ATT&CK framework version, right? But it's basically it's been adopted as a standard already, basically. So I really recommend checking that out. So you have the link there. And one last thing is I've created, because I've been studying Kubernetes for I think over 6 months already, and trying to really understand how it works and also how to protect it, right? So I created a GitHub project that's basically free, with a lot of information and links on how to start your Kubernetes journey, right? So basically, okay, how do I learn? Some links for trainings, for videos and books, even free books available on Kubernetes, and some stuff specifically focused on Kubernetes security. And feel free to start the project, fork it, and if you have a new link that you found that you think it's awesome, you can also submit a pull request to me. So that's it for my talk. I hope you guys enjoyed, and thank you, everyone.
Awesome. Thank you. It's as with anything Kubernetes, there's a lot of information. One of my biggest concerns about the security associated with Kubernetes is just the vast amount of surface there is, the vast amount of configuration, the differences between different managed services, as we see the difference between GKS, AKS, and EKS. It's actually, if you can still share your screen, I want to ask you a question. You have to tell us about that image.
Yes. Okay.
So I know in your slide deck you did have some information about it, but you have to say something about that image.
Which one?
On the main screen on your title slide.
Oh, title slide?
Yeah, the graphic.
Okay.
Which is, I gather, not an explosion in a spaghetti factory.
Yeah, this one?
Yes, tell us about
Yeah. No, this is just a template from Trend Micro where they created some designs, some very neat designs and arts on the data information that they had for like security attacks, malware, and stuff like that. So they hired like a designer to try to create a representation of that information that we have on all the security stuff, right? So there's different graphics, but it's just like a template there. It's not related to Kubernetes.
Right. Okay. So it's still based on attack data.
Yeah.
Okay. I saw that, and I had to ask.
Mm-hmm.
Now, one of the comments we actually had in the chat stream was talking about deprecations of PSPs, and apparently there are discussions to deprecate PSPs in 2021. And I was wondering if you knew anything about that and could share anything on it.
Yeah, I've seen some discussions about that. It's not I think official yet. I just recently joined the Kubernetes, the CNCF SIG security group, which is the special interest group that talks about security. So I'm part of that. I'm helping like move security settings, not just of Kubernetes, but all the CNCF projects as well to improve those settings. But yeah, I've seen some discussions, but I don't think nothing is defined yet. So I'm not sure right now. It's still, I think it's still the best solution that you have out there for free, unless you have like you have budget to buy a solution that would be something like CSPM solution for Kubernetes, or something that would monitor your cluster and report on any misconfigured issues, right?
Right.
We also just released, and I can send the link here. I'm not sure. We just released yesterday the Cloud Native Security White Paper, right? Which I was one of the reviewers of this white paper, and it's basically a white paper talking about how to apply security on cloud native environments and cloud native applications, right? So I really recommend you that you guys check that out.
Right. The next question I have is a question I really have to ask.
Sure.
I can't stop myself from asking, but not all cloud providers and managed services are equal.
Mm-hmm.
I have had some experience with Azure, but not with GKS or AWS yet. I'm just wondering if you've had experience across different platforms, and if you felt that their posture was if there was any particular, at this moment in time, a preferred security posture.
Okay. So yeah, spoiler alert, that's one of my next research topics. Is basically comparing those different managed services and comparing on a security perspective, right? And evaluating their defaults, what best configurations they have. So probably I'm releasing either end of this year or beginning of next year an article about that. But so far I've tested only on EKS, and I'm beginning to use the Azure one, the AKS.
Mm-hmm.
And GKE would be the next one. So I don't have any like data right now to share, but I should have that soon.
Well, watch this space. Well, we know what your next presentation will be.
Sure. Yeah.
Awesome. Thank you so much, because we know that everybody's having to face the onslaught of Kubernetes information, and it is non-trivial, and it is a complex environment. And my experience has always been that security abhors complexity. And so, as your reference to the Shodan finding 2,600 exposed etcd setups, that proves to me that this is no different. So thank you so much for presenting this to us. It's been a lot of information and very insightful. So the information has been absolutely awesome. So thank you for your presentation.
Yeah, thanks for having me. Yeah, great.
Awesome, thank you. moving forward in 2019, we're not sure when our next presentation will be. We'll other than potentially in January. So watch for our announcements, watch for our meetup announcements, and watch our Twitter site. And you can always check us out on our Slack environments. So feel free to reach out to any and all of us. And we hope you stay safe and have a very safe rest of your November. So take care, and thank you very much.